All right, graphing polynomials. So we've done tons of stuff with polynomials, and now we're going to graph them, which is why we were doing like all the graphing and stuff last unit, okay? Polynomial. That was super stupid. Okay, so a polynomial function, we've gone over this a bunch of times, but polynomial, poly means many, and nomial in this case means term. Nomial has different meanings, but in this case it means term. So really polynomial means many terms. So polynomials can have constants, variables, and exponents. They can be combined with addition, subtraction, and multiplication. We've already done those ones, and we're going to be doing division. Except for you can't divide by just like one variable. So like 2 over x is not right. Okay. Oh, whoops. So a polynomial can have constants, variables, and exponents, but never division by a variable. Okay. And it can also have many terms, but they can't be infinitely many terms. So it can't go on forever. So if we're looking at these and we want to know whether or not it's a polynomial, well, the one on the left is a polynomial. The one on the right is not because of the negative exponent for this one. And then because this one's being divided by an x. Okay. Some more examples. So these are all polynomials here. 5 is a polynomial because it's just a constant. Okay. These are all not polynomials, and it gives some reasons why. The first one is not because of the -2, which is the same one that we just talked about. The second one is not because of we're dividing by a variable. Again, same one we're talking about. 1 over x, same thing. And then square root of x has an exponent of 1/2 if we converted that, which is not allowed. So that's why that one is not. Okay. But these ones are allowed. So like x over 2 is allowed, 3x over 8, and the square root of 2. And x over 2, well, that can just be rewritten as 1/2 x. So that's perfectly fine. Same reasoning for the 3x over 8. Well, that can just be 3/8 x. And then the square root of 2 is just a number. So we can use that. Versus this was the square root of a variable. Different. Okay? So classifying these, we have monomials, binomials, and trinomials. Okay? A monomial, that's just one term. Think about like a monocycle, like you've seen, or people call them unicycles also, but you're just like riding around on one wheel. Bicycle or a binomial, that's 2 terms. Trinomial, tricycle, tri means 3. We also have quadrinomial and quintinomial, but we don't have to use those names. Okay? Anytime, if it's over 3, just call it a polynomial. Okay, and what is so special about these? Well, we can add and subtract them, but we can also graph them. And their graphs are they're easy to graph. They have smooth and continuous lines. Okay. You can also divide polynomials, except for the result isn't always a polynomial. Okay. All right, let's look at the end behavior of these. So we have already talked about end behavior of just normal graphs. So let's look at these graphs. So notice here, like the end behavior of this first one would be, well, it starts down and ends up, right? This one, the third one is also starts down and ends up. Same with the fifth one, starts down and ends up. What do we notice about all these? Like this is technically to the first power. This is to the third power. This is to the fifth power. So it looks like all of the odd exponents are opposites of each other. All the odd exponents, the end behavior is opposite. Okay. Well, let's look at the even ones now. So all these even ones, they're both going up, right? Same thing here. And same thing here. So all of the even exponents are the same end behavior. Okay. So I think I wrote this out in different words here. Even exponents, the ends go the same way. odd exponents, they go opposite ways. And I always remember this like odd, opposite, and then even, they just go the same, okay? So if we're given f of x equals x squared, both of those are going up, so they're both positive, right? What if I was given f of x equals negative x squared? Well, that flips our graph down, and now they're both negative. Okay, so the negative in front of an even exponent is going to make them both go down. And if it's a positive, they're both going to go up. Now, if it's an odd exponent and it's positive, it starts negative and it ends positive. It will always end with whatever the sign is. So if the sign's positive, it ends positive. If the sign's negative, it will end negative. So this one, this was a typo. There should be a negative right there. That should be negative x cubed. I'm just going to rewrite it, negative x cubed. So for this one, it's odd and it's negative, which means that it's going to end negative, but it's going to start positive. Okay, and let's put this all together now. So here, if it's even and positive, they both go up. If it's even and negative, they both go down. If it's odd and positive, it starts negative and ends positive. If it's odd and negative, it starts positive and ends negative. I had a math teacher in high school who called this the good. So the good, they're both going the same way. So the good would be even and positive. The bad would be even and negative. They're both going down. And then the ugly, we have to decipher which ugly it is, but these are going opposite directions. Okay, kind of a fun way to remember it, I guess. So here is a chart. Highly suggest you draw this chart somewhere. Okay, so this is our degrees right here. So it's either an even degree or an odd degree. And then leading coefficient is either positive or negative. And this is telling us what the ends are going to be doing here. Okay. So if we're given this function here, and we need to figure out the end behavior of this. Well, we're just going to look at the highest exponent power. Everything else I don't care about. I'm just going to look at my highest exponent power. So I have 3x to the 5th power. Well, that is a positive leading coefficient, and it is an odd degree or an odd exponent. So positive would be this one, and odd is this one. So I'm guessing that the end behavior is going to look like that. Okay. So that is, as x is going to negative infinity, f of x will be going to negative infinity. And as x is going to infinity, f of x is going to infinity. And then there's just a sketch of that graph, so we can see that we were right. Okay? And we don't care when you're dealing with end behavior. We do not care about what's going on in the middle. We just care about the outsides. Okay? This one, so negative 2x to the 8th plus blah, 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 blah. Don't care about all that. I only care about that 2x to the 8th. It is a negative leading coefficient, and it's an even exponent. So negative and even means that they are both going down. So this would be as x goes to negative infinity, f of x goes to negative infinity. And as x goes to infinity, f of x also goes to negative infinity. And there's a sketch of that graph so that we can kind of see that. Okay? Cool cat. Okay, let's get into graphing these. So first, we want to classify this, and you can it's either a trinomial, or we can also call it a quadratic. Quadratic is when it's squared, right? So this is going to be some sort of parabola. Now, I'm going to pull out, before we pull out our calculators, we want to figure out the end behavior. So here, this is an even exponent, it's a positive leading coefficient, which means that this is the good. So the end behaviors will both be going up. So as x goes to negative infinity, f of x goes to infinity. And as x goes to infinity, f of x goes to infinity. Okay. Now I want to find my maximums and my minimums, and we're going to use calculators for this, okay? It's important to be able to like graph in the calculator. We won't always use it, but especially for ones like this, let's graph them. So let's look at this calculator right here. Okay, let's see. I'm just going to zoom in on this. Okay. So over in my y equals, I'm going to put this in. So x squared plus 2x. And you should all have calculators like this, so I'm hoping that seeing this will help. But then I'm just going to push graph. Okay, and there is the graph of that. If your window is weird, you can push zoom 6, and it will fix your window for you. Mine wasn't weird, so we're okay. But looking at this graph, I can see that there is no maximum point, right? So our relative maximum does not exist. There is not a relative maximum. Okay. Well, let's see about, there's a relative minimum, right? The relative minimum would be right there. Let's figure out what that point is so that we can put it on our graph. So if we push second trace, and then you go to minimum right here. See how we have this like little blinking cursor here? Well, I can move that over to the left. And you can just do that by clicking this button. And push enter. And then move it over to the right. So it'll be right of there. And push enter. And then we're going to push enter one more time. And that gives us a relative minimum at negative 1.99999 and negative 6. So this is really like negative 1. So our relative minimum is going to be negative 1, negative 6. Okay, and then we can graph that on this graph right here. Okay, and it looks like we also have zeros here. Let's find those zeros. Okay, let's find the zeros. So to find the zeros, we're going to go second trace. Use second trace a lot. And then go to 0. Okay, and then we're just going to move this over to the left. So it's above the x-axis, and we're going to push enter. Move it to the right. So it's below, and push enter. Push enter one more time. And we get this negative 3.440. So one of the zeros is negative 3, 0. So we can graph that on here. And to find the other 0, we'll go second trace, 0. Then we're going to move this to the right. But we want it left of the x-axis, so we're going to start below the x-axis. And then we're going to move it above the x-axis. And then push enter one more time. And it looks like we got 1.440. So our other 0 is at 1.40. Okay, and then that's all we're going to do on the calculator. The rest of this, we're basically done graphing this at this point. So let's just go back to this. So now, there's our graph. And we can finish by finding increasing and decreasing. So increasing, remember, increasing isn't when you're walking uphill. So increasing, domain and range would be, domain would be negative infinity to infinity. Range is negative 6 to infinity because it's a point at negative 6, so that's where there's a bracket. Now, increasing is where you're walking uphill, so that's going to be negative 1 to infinity, and it's always x values. Okay, decreasing would be negative infinity to negative 1. Cool. I think we're only doing one more, so let's do this one. So this one is a cubic because it's cubed there. It's to the third power, which we could also call, this is still a trinomial because there's only 3 terms. Okay. So then end behavior here, this is an odd exponent and it's the negative leading coefficient. You gave me the ugly. So this is the ugly. So it's going to start positive and it's going to end negative. It always ends the way that the x or the coefficient is. So this is going to be as x goes to negative infinity, f of x goes to infinity. And as x goes to infinity, f of x goes to negative infinity. Okay, and then let's pull out our calculators again. So then here, whoops, that's not what I wanted. Let's put this into our calculator. So if you go back to your y equals, and we can just delete this out of here. We have negative 2 x to the third power plus 8x minus 1. Okay, and then I'm going to just graph it. Whoops. What was my error? I put a subtraction sign instead of a negative sign. Make sure you put a negative sign. This is our negative. So if we graph this, it looks like that. Kind of pretty. Okay, so we need to first let's find our maximums and minimums, okay? So this right here is a minimum point. So if we go second trace, and then go down to minimum, we can move this over to the left of that low point, then move it to the right of that low point, and then push enter. So it's negative 1.2 and negative 7.2. So our minimum is negative 1.2, negative 7.2. And we're going to graph that right here. Okay. And then we're going to find our maximum. So it's kind of like, it's really nice that we have these calculators that can do this for us. So then, or else you have to use calculus to find the minimums and maximums, which obviously we are not in calculus. So this is kind of like an intro to what you'll be doing in calculus. But enter, you just find, in calculus, you can find these without using a calculator. Fun stuff. And then enter, and then there's that high point. So that'd be 1.2 and 5.2. So our maximum is 1.2, 5.2, which we could graph right here. Okay, then I also want to find these zeros here. So let's just find those. So if we go second trace and then 0, let's find the one to the left first, this left one, the first one. So we want to be left of the x-axis, so right there. And then we want to go right of the x-axis, so there. Enter. You have negative 2.1. If this pops up right here, that is infinitely close to 0. This is saying negative 2 times 10 to the negative 12th power. So that means I'm taking negative 2. And I'm moving this decimal over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this would be like 0.00000. So basically, this is 0. Okay. So then we have 1 0 at negative 2.10. And then I can graph that on here. Let's find the next 0. So second trace, 0. Let's find this middle one. Which would be at 0.120, which is essentially 0, 0, but that's going to be right there. And then let's find the last one, second trace, 0, and then we're going to move this over. So left bound right there, right bound right there, enter. And again, we have that 1e thing. It's 0, so it would be 1.90. Okay. Then we can just finish graphing this. I don't need the calculator anymore, so let's just graph this. Looks like that. So then our domain here is negative infinity to infinity. Our range is also negative infinity to infinity. And then this is increasing from negative 1.2 to 1.2. And it's decreasing from negative infinity to negative 1.2, and then from 1.2 to infinity. Cool? Okay, see ya. Okay, bye.